So we're going to take a look here at example number 2, and we're going to try to use this fundamental theorem of line integrals to help us. So I want to find the work done by this vector field on a particle which moves along some piecewise smooth curve that starts at 0, 0 and ends at 1, 0. So all I know at the moment is that I'm going to have some curve that starts at 0, 0 and moves all the way out to 1, 1. But notice I'm not told the path. I have no idea what the path is. It could be a straight line, a curvy line. It could like loop around in circles for like forever. I don't know anything. I just know the start and the stop point. But if I think about what the fundamental theorem of calculus, or fundamental theorem of line integrals, excuse me, says, I can easily make some really, really quick determinations. All right, I can go ahead and state the following. Let's see what the theorem said. If it's the case that I can express my work integral as a gradient of a function dot dr as opposed to regular f dot dr, then I can evaluate that function at my endpoints. So here I can start by saying that we know that the work is going to be equal to, moving along the curve C, f dot dr. And I'd really like to find a potential function for that f. So maybe I'll state this. We see that if f of xy is equal to, I'm going to go with the following function. How about x comma y? And you can see why I've chosen this function, because if I select this, then can you quickly determine for me what would be the gradient of f? So think, what would be its partial derivative with respect to x? It would be y. Partial derivative with respect to y? It would be x. And so this actually turns into my f function. So my gradient here of f gives me exactly my capital F. So this means that now I have found a little f that works for my fundamental theorem. So by the fundamental theorem of line integrals, we can say that the integral for my work along C of f dot dr should indeed be equal to the integral for gradient of little f dot dr. And then that says I should just be able to go to my f function and kind of evaluate at my stopping point and subtract what happens at my starting point. Now, if I go to my function f, which is defined right up here, and I say, what do I get when I plug in 1, 1? Well, I get 1. And what do I get when I plug in 0, 0? I get 0. And so, boom, I end up with 1. So this is really, really powerful. What this shows us is that that opening question we had at the beginning of the section can definitely be answered with a yes. Is it the case that no matter what segment or what curve I take to connect 0, 0 to 1, 1, if this is my vector field, then yes, the answer is always 1, and the path is completely not important. So when applying the fundamental theorem of line integrals, what we'll see is that the most challenging part is often finding our f, right? Finding that function whose gradient equals our vector field. In some cases, that function might not even exist, and it might be really, really hard then to try to evaluate certain line integrals. But if I can evaluate or determine this little f, fundamental theorem of line integrals saves me a whole bunch of work. So this is a really, really powerful idea. We'll take a look at another example in the next video.